So in the first part of this video lecture, we saw a function, a magic formula. The formula in itself is not very important. What's important is there exists a sequence of functions with these properties. Each one takes finitely many values. They are non-decreasing in the parameter k, these functions, and they converge for each point x, they converge to x as k tends to infinity. Well, moreover, gk of y is larger than gk of x for y larger than x, but I'm not sure we're even going to need this property. And now in the second part of this video lecture, we're going to show how we can use the approximation of the identity to make an approximation for non-negative extended Borel functions in general. So if we have f, here's the graph of f. Well, in the picture here it's called x because this is an old picture. If we have the graph of a function f and we want to approximate this function f by one which is a simple function, by one that takes only finitely many values, how can we do that? Well, we can use the approximation of the identity that we constructed already and apply it to f, or compose it with f, which means for each point x, we have a certain number f of x, and we just bring it lower here to the one of these points, the points where the function gk can take values. So this is what composing from the left with gk does to a function. The function used to go like this, and now for each x, you're just taking out of this set of possible values that you allow gk to take, you're just lowering your function until that point. So all this will be lowered to the rounded down to the closest interval from below, except that here if the function continues increasing too much, it will be kept at this value here because this is the largest value that g2 can take. So this g2 composed with f. So again, from the fact that we can approximate the identity, and this gk, it's something that operates on numbers. It just takes a number and rounds it down, or even an extended number, non-negative, and rounds it down to the closest point in this discrete set that is below it. So this is an operation on numbers. And now if we have an operation, a function f that goes from an abstract sample space or measurable space to R plus, including infinity, no problem. So we can approximate f by a simple function by doing the following. We bring this down by composing with gk, and this will give us real numbers, finite numbers, and well, we can define the composition directly. If we define the composition directly, this will be gk composed with f. So this is an approximation for f, and let us go back here by this property. By this property here, these are functions. If we call this fk, we have 0 less than or equal to fk, so fk is non-negative, and it increases to f. And these are simple functions. So we can always find a sequence of simple functions that approximates whatever given function f we have, and approximates like that. And as discussed in the first part of this video lecture, this is extremely convenient. So this is the first take-home message. It is for every non-negative extended Borel function f, we can find a sequence. So all those theorems that said if a sequence satisfies this or that, now we know there exists one. There exists a sequence of simple functions fn, non-negative. So let's add here to the statement non-negative simple functions fn such that increase to f. This is the first take-home message. The second take-home message is any other definition that we could give of an integral for non-negative extended Borel functions, any other definition would have to be the same. Just assuming nothing more than it being unitary and sigma additive, it has to be the same. And why is that? Well, sigma additive together with linear, once we know that it's linear, sigma additive is the same as satisfying the monotone convergence theorem. And why it would have to be this one? Because, well, again, because given a function f, we can define the integral of f to be the limit of the integral of fn the mu for any sequence fn that increases to f of simple functions. And we already saw that the integral of a simple function, we don't have any choice on how to define it. And now we don't have any choice on how to define the integral of f either, because either this, what I just wrote, will be the definition of integral as some book done in some books, or it will be a theorem. So whether it's a definition or a theorem, this is something that follows, this identity here follows from the assumption that the integral is unitary, linear, and sigma additive. And this concludes this video lecture, which will probably be shaking your heads a bit.